Thank you, Moshe. As he said, I am Sampat Kannan. I've been officially the associate director here for the last 2 weeks, but I actually started the job a little bit earlier. I know I was unofficial, under the radar associate director until July 1, and then yeah. But welcome to the Simons Institute. I guess you probably all know because you've been here for other workshops. But I want to tell you briefly about the Simons Institute. It was founded by a grant from the Simons Foundation in 2012. And that Simons Foundation has been sustaining us up to this point and will continue to do so for the next 10 years at least, as far as we can see. So in the Simons Institute, the goal is to bring together researchers in all branches of theory for an intensive semester where we can foster collaborations and have, young people, young stars of the future, as well as leaders of today, talk to each other in a very intense fashion. But it's not only about the study of theory and computation for its own sake, but the Simons Institute also wants to bring the lens of algorithmic thinking, computational thinking on other disciplines. We've had many workshops, and programs in computer science and physics, in the world of quantum computing, computer science and economics, computer science and social sciences, and so on. So we are very much looking outward as well as inward. And I think this program is a great example of connections between maybe two kinds of theory, at least here, hopefully, if not outside. Thank the organizers, Moshe chiefly and Rujika, for putting this program together and for this workshop as well. Look forward to a great workshop. It's a less intense workshop in terms of the schedule. So I hope you'll profit from this and have more of an opportunity to talk to each other, maybe solve an open problem by the end of the week. That's all we ask for. Let's see. So a couple of ground rules here. Moshe already mentioned we have this rather draconian policy here, which seems unnatural to most participants, of no food or drink in the auditorium. We've managed not to need to reupholster the chairs for 10 years because of that. The other thing is that our staff is basically running a workshop every week for the last 10 weeks. So one thing they really appreciate is to be able to close up this place on time at 5 p.m. and leave, because they don't want to be waiting here late every day. So we request that if you want to continue your discussions at that point, just step outside there and let them close up the auditorium. Well, have a great workshop, and I hand off to Moshe.
Thank you, Sampat, and we are grateful for the Simons Institute for hosting us. So some of you were here 2 weeks ago. We had another workshop, so you'll hear me say part of the same thing. So in 2018, Thomas Colcombe and Marta and Ruzika and I wrote a proposal for the Simons Institute to have a program on theoretical foundation of computing systems. And we also pushed that usually Simons Institute tend to host volume A activities, not many volume B activities. And proposal was accepted, and we were supposed to be here in 2021. But something small happened, and it was called COVID. And so everything has to be virtualized. So we kind of did as well a job as we could. For example, we turned every workshop into a weekly seminar, because nobody can sit on Zoom like 5 hours a day for 5 days. So we kind of spread it around. And during the spring of 2021, God knows how many hours are spent on Zoom. And I remember nothing. Okay? And so when we got an opportunity to meet here in person for a reunion, which is a bit strange because, yes, we are reuniting after being on Zoom, Ruzika and I jumped on it and we took the program. So some people here are participants in the 5 weeks, or some period are coming here for the summer, and some are just invited for the workshop. We scheduled the workshop to be really not just a conference. So it's basically the workshop we have lectures in the morning. Today we will have lunch there, I think. There will be box lunch. Today we'll have lunch there. Every day after lunch, we are inviting people to come back and we call a panel. We'll put all the speakers here and we can have a discussion, like a workshop. People can ask more questions and we try to organize 2 weeks ago, we tried to discuss in groups. It didn't work very well. So this is all going to be big discussion group. 2 weeks ago, we have Houston weather in Berkeley. I was so relieved last night. It was so nice and cool. I enjoyed the walk from Bart here as opposed to coming sweating like it was 2 weeks ago. So again, if you have a question during the talks, brief questions, ask, but the morning schedule is pretty tight, but we'll have plenty of time in the afternoon. And there is one activity that I did not see listed in our program, but on Thursday, 4 o'clock is on Thursday, the Richard Karp lecture. So on Thursday afternoon at 4 o'clock, we will have a tea at 3 o'clock. And at 4 o'clock, I will give a talk, kind of a computational lens, called Efficiency versus Resilience, and you're all invited to come to the talk. Ruzika apologizes, but she has to be on call to NSF, and since these guys give us money, when they said be on call, you're going to be on call. And now I'm very pleased to start with the first, in the morning we'll always have 1 hour talk, and we're going to start with Laurent Doyen, who is going to tell us about new model for game with incomplete information. Please, Laurent.
Thank you. Can you hear me well?
And where is my microphone runner? Right here. Sit in front.
Thank you, Moshe, and thank you so much for organizing this and for inviting me. So today I will talk about new models of games with imperfect information. And I want to start with a reminder, or what I expect for all of you to be a reminder of why we use games in system design, or one of the reasons, which is reactive synthesis. Okay, sorry, I forgot to say that it's a joint work with Dietmar, and which is my office mate, and Thomas, who is our student. But yeah, sorry. So reactive synthesis, I just want to make a reminder, and I think this is very familiar, but just to fix the context. So the goal is to synthesize, to design a program, which we call a reactive program, and it is this box P here. So it takes as an input a sequence of symbols from a finite alphabet, and we take the sequence to be infinite. And as an output, it produces also a sequence of symbols from a finite alphabet, which is also infinite. And then the only thing we want to do is to satisfy some sort of a specification, which I call phi here, and which relates which input and output behaviors can go together and are considered acceptable or correct. This is a very general setting, and there is just one restriction, that we are in a synchronous setting, which means that each time you get a new input, you have to produce a new output. You cannot wait to have the whole sequence and then produce it. And so I call this condition P to be sequential, which means, if you have a finite sequence of input and you add a new one, the output will just be the previous output plus a new output. So each time you get a new input, you produce a new output. It's a synchronous tick-based system. And so the synthesis problem is to construct this P such that whatever the input is, the image of the output satisfies, together with the input, satisfies the specification. And this immediately corresponds to a game where P is producing the output, so P is the program, and is playing against an opponent who is choosing the inputs. And the goal of the program is to satisfy the specification. So it's P as a winning strategy if the combined input-output satisfies the specification. And this dates back to Church in the 60s. It's called the Church synthesis problem. So this is a very standard thing. So this is a game of perfect information. This is the usual game we are used to. And since I want to talk about games of imperfect information, I will now show you the picture that I would illustrate for games of imperfect information. And this is just this picture where I just added a box here, which I call a white box, because we know what is inside. It's like some designer has already constructed this box, but we know what is inside. So the only difference is that this program now does not receive directly the input, but the transformation of the input by this box. So you could think of it as another component of the system, but it could also be a sensor. It receives information from the environment, and it gives you some information about it, but it's filtered. And now, as before, we have a specification that we want to satisfy. For every input, the output should satisfy it. And now it's still a game, but it's a game of imperfect information, because there might be different inputs, x and x prime, that give the same image by this box. And then this guy does not know the difference, cannot distinguish between whether we are in the input x or in the input x prime. So it's a game of imperfect information. And this is a formulation or a setting that dates back to Reif in the 80s. And that's basically the status of games of imperfect information so far. And now I want to go beyond this, or share with you some ideas. And well, we have I call it a research program. Maybe it's a bit ambitious, but we have, with Dietmar, so my office mate, we have started this program many years ago, and we have taught a lot, and we had many ideas, but nothing very, formalized. And now we have like more precise ideas, and I want to share it with you. So there is a whole list of things, but I will not cover all this. I just want to give you a broad idea of the kind of thing we are interested. And the first thing is, well, we'll present this today, this abstract model of games with imperfect information, something like that I want to illustrate today. But there is also a more concrete or more applied model, which we call full information protocols. And this is more related to distributed synthesis problems and more towards application, I could say. And this model is like an instance of the abstract model. So it will help to also grasp the notions. And then once we have these new models, then there is a natural set of questions that you want to solve, and this is what I list here. So the first thing is expressiveness. You want to compare this model with existing models, compare how much are they really different, do they express different things. Then central to the game issue is the strategy synthesis problem. You want to construct strategies for the players. And here I will not talk about it at all, but I will just mention that we have basically for the abstract model, we can show it's decidable if something is true. So like we have a sufficient condition, but we don't know if it is satisfied in general for this model. But we will show that for this model, it is satisfied. And so at least for the application, we have a decidability results. And then related to that, you have all the usual question of how much resource do you need to solve all these problems? So decidability is one thing, but what about the complexity of the problem? What about how much memory you need to win the game? What happens if you use randomization? What about if you limit the communication between different systems and so on? So all these questions are there. And some of them we have addressed, but by no means. And as I said, we started this many years ago, but you see that there are only 3 papers for the moment, and only 2 of them are really published. And so it's really a work in progress, and we could say a bit slow, but yeah, we are only 2 also, and our student joined only recently, so yeah, it's a lot of work, but yeah, we are moving somehow slowly. Okay, so now I will really start the talk and present the model of games with imperfect information. In some sense, for that, I have to define the model of games, which is something, again, that I hope most of you will know already. You can call it infinite repeated games or Gale-Stewart games, or maybe some people are familiar with games on graphs. All these are the same things. And then I will add on that imperfect information, talk about expressiveness, and then present the application model. So I want to present an abstract model of games, but to illustrate, I will use a very concrete game, which is chess, but you don't need to know anything about chess. It's just to illustrate. And I also don't want to solve chess. So our games will be 2 players, turn-based, so player play in turn, and then there is perfect information for the moment, which is the case of chess, right? So now the game, I will not play it on the chessboard, but we will play it on a sheet of paper, where the player will just write their move like this. So player 1 plays an action, player 2 replies, and so on. And these things are from a finite alphabet, like basically the source cell and the target cell of the piece that they want to move. So I call this an action and a response of player 2. And all together, this form a move. This is the terminology I will use. And so because we are on the sheet of paper, every action is legal. So it's not really the game of chess for the moment. You can just play any string that is in the alphabet, and the other guy can respond, exactly like in the church synthesis formulation. There is an input, there is an output, and so on. Yeah. So then the question is, who is winning? And for that, we will play for infinitely many rounds, and we call an infinite sequence of moves a play. And then we need to define a winning condition, which will just be the language of infinite sequence of moves that are correct. And this is an omega language of winning plays. And this now you can use the chessboard to define it and say that, for example, if you reach a checkmate, then whoever wins.
The synthesis competition. Solve chess.
Yeah, sure. Yeah, of course. Yeah. So, and then, okay, so then one more thing. So yeah, now you execute just the sequence of moves in the chessboard, and then you can know, I mean, you have basically a graph, a configuration graph of the chess, and then it tells you who is winning. And we can incorporate in this whether a move is legal or not, right? If you go out of if you move a piece that is not possible, then you lose immediately. So it is not a problem to encode legal moves into the winning condition. So now we have a very simple setting where there is no, where you can play whatever you want, and just the winning condition takes care of it. So now to summarize, the only thing we need to define a game is a finite set of moves, which I call gamma in the rest of the talk. And you can think of it as a combined action of player 1 and response of player 2. So that's a move. And then the only thing you need is a winning condition, which is in general just a set of infinite sequences of moves, those that are winning for player 1. And if you want to fix the IDs, you can take it as omega regular, and then there is a finite representation and so on. But most of the things that I will say will actually hold for arbitrary winning conditions, but you can fix it like this. Again, this is Chur's formulation. And now how to model imperfect information. Well, we will just specify what I call an indistinguishability-relation, which is a subset of pairs of histories. So a history is just a finite sequence of moves. This is the current state of the game. Now you have played for finitely many steps, and you are at a history. And this relation says when two histories are indistinguishable for the player. So if you have TO1, TO2 in the relation, it means that when you are actually at history TO1, the player may believe that you are in TO2, but it can also believe that you are in TO1. Yeah? So these are the indistinguishable histories. And now the question is how to specify such a relation, because this is in general an infinite object. And so there is two models, and that's okay, so there is the first model, which is called the observation model, the traditional model that exists since Reif, basically, what I presented at the beginning. And then there is this new model that I want to introduce, which I call the distinction model. So this is how to specify an indistinguishability relation. So I'll start with the traditional model. So in the traditional model, there is this transduction that was the white box in the picture. And here in chess, you could imagine that instead of seeing exactly what the opponent is doing, you may see only, like, for example, which piece has been moved, actually which type of piece has been moved, like a pawn, a queen, a bishop, but you don't know from which state to which state or which cell to which cell. And so it's more difficult to win. Yeah. And in general, this will be defined by the transduction that transforms the sequence of moves, so gamma plus, into a sequence of observation. And we also want it to be sequential or length preserving. Each time you get a new move, you get a new observation. So you can see the tick, the time passing, and yeah, that's what you get. So now I will, so now you can define the induced indistinguishability relation between histories. It just says that two histories are indistinguishable if they have the same observation by this transformation. And now I will go away from the example of chess and just use abstract moves and abstract symbols. So this is another example of a transduction where A's and B's are the moves, so they're in the gamma, and 1 and 2 are the observation. And so when you want to know the observation of a history, you just read the history in the automaton, and then you produce the outputs. So for example, you say A, B, 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 so you'll do A, you produce a 1, then B, 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 you will produce ones. So you'll get observation 1, 1, 1, 1, which is here. Yeah. Now, if you take another history, for example, B, B, A, A, B, B, A, A, you also get all ones. So those two histories produce the same sequence of observation. They are indistinguishable. That's how you define this relation. Yeah, and this is the model of Reif, observation model. Now, one idea is to define this indistinguishability relation in a different way, but also very natural, I think, which is directly by an automaton that will read two histories and tell you whether they're indistinguishable or not. So an automaton that reads two histories at the same time, I call it a two-tape automaton. And since you read the two histories at the same time, you can also see it as reading it reads the first letter of the first history and the first letter of the second history, then the second letter of the first and second letter, and so on. So you can see it as just a normal automaton that reads pairs of letters because it's synchronous and the two histories are of the same length, so you can just read two letters at a time. And then you just say that two histories are indistinguishable if they are accepted by the automaton. So now this indistinguishability relation is just acceptance of a pair of histories. And then we will say that the histories are indistinguishable or they are companions. This is the terminology we use. And here a small example. So this is a two-tape automaton. So it reads one letter on the first tape, another letter on the second tape, and you have all combinations. Just I use the star here to mean any letter. So this means AB or AA. And the X is just a rejecting state, which is a sync state. So it's, these three states are the same state, but just for the visual, I copy it. And now if you want to know if two histories are indistinguishable or not according to this model, you just read the two histories synchronously. So for example, here, the same histories, ABB and BBAA, you will read AB, BB, BA, BA. And if you end up in an accepting state, then they are indistinguishable. So this is the case here. It's indistinguishable because it's accepting it ends up in Q4. Now we need to be a bit careful with this model because there are some conditions that apply. We cannot just use an arbitrary automaton to define a reasonable indistinguishability relation. So the first thing, okay, it should be synchronous and length preserving, but that's the case because you will always read one letter on each tape, so that's fine. But the second thing we want is what I call perfect recall, which means I know what I knew. And this means that if I knew at some point that I was in two different situations, TO1 and TO2 are indistinguishable, then it doesn't matter how I continue. In the future, I will always know that I cannot confuse TO2 with TO1 or any continuation of TO2 with any continuation of TO1. So for all continuations, if I continue TO1 and TO2 with anything, they will also be indistinguishable. They will also be distinct, yeah? I can distinguish them. And so that's one condition. And then it should also, maybe we have this intuition that it should be an equivalence. Right? If I'm TO1 and TO2 are indistinguishable, then TO2 and TO1 are also indistinguishable, and there is transitivity and so on. But this is not necessarily the case if you take an arbitrary automaton. So we need to ensure that these conditions are satisfied, otherwise it doesn't make sense. Yeah.
If two things are indistinguishable, you extend them with the same history, then they should be also indistinguishable rather than, I mean, I can get into indistinguishable from two places that was this, there's nothing wrong with that.
I'm not sure because you could, I mean.
We are being recorded, so do the mic.
Should I repeat?
Yeah, please repeat.
Okay, so I was asking that basically my question was whether these two are equivalent. I start from two indistinguishable places. I extend them by the same word, and I should still be indistinguishable. That is one consistency kind of criterion that makes sense to me.
But, okay.
If you were in a place you couldn't tell the difference, you extend it with the same thing, you should still not be able to tell the difference.
But maybe your intuition is about observations. If you observe the same thing, if you have observed the same thing so far, and now you observe the same thing, yes, you cannot distinguish. But here we are talking about the histories. So the TOs, they are gammas, they are not sigmas, they are moves, and the moves you don't see, a priori. You only see the observations. So now I'm talking when two sequence of moves are indistinguishable or not, and you don't observe them. You observe something else. I don't know what you observe, but here I don't specify the observation. I just specify when you are indistinguishable or not. And so there is no reason that if you are...
It's going to be very special DFA. Basically, it has to be all sets are accepting.
Yeah.
Unless you go to false. Yeah.
Exactly. Yeah. This is a very special DFA. Yeah. But it's important to get the intuition, I think. So I don't know how to, because so.
No, this is called in the reasoning about knowledge. It's called perfect recall, no forgetting.
Yeah.
So once you know that they are distinct, we don't forget.
Yeah. Once you know that you are in different situations, how you extend, you will know that you cannot be confused with something that you knew that was different, right? So.
But in a generic game.
Yeah.
I can get two sequences of moves, get to two different places, but I can have different but converging set of extensions get to the same place. Maybe my intuition is wrong, but this is why I was not sure if you can pick any two for all row 1, row 2. I'm not permitted ever to converge again. It seems a little strong.
Okay, somebody wants to interfere.
But doesn't it just work? So you started with two sequences. You ended up in a certain state of the automaton, and then you just you extend with one computation. So I don't see what.
You don't see my confusion.
Yes, okay. I mean think of the model with observations. If you had different observations, you can already know that you cannot be confused between these two histories. They have the different observations. So now it doesn't matter how you continue. The sequence of observations will be different because they are already different in the prefix. So that's the idea. But here I talk about histories, not observations. So, I hope it's, question,
You said that the DFA, these are very special. Yes, I see it. Will you present some structural conditions?
I'll talk about it. I will now explain how these conditions, how we check them. Yeah, that's the next thing. Yeah, and what does it mean? I mean, yeah.
What if the reason that I'm able to distinguish two prefixes two taus is that in one I've made one observation and in the other I've made two observations, then I think this doesn't apply. I can later extend it so that they become indistinguishable again.
So you mean the number of observations would be different?
Yes, and I'm counting the number of observations.
No, but yeah, this is a restriction we have, that we are synchronous. It's always, each time there is a tick, there is one new observation or one new move, but no difference in length. Yeah, that's not allowed. That's a restriction. Yeah.
No, but I think what, if I can amplify, is it's synchronous.
Yes.
But on one sequence I saw one A, and the other one I saw two A's. So I said they're different. But then I see another A on track one. And I said, oh, they're okay.
No, but you have to see something. So if you say I see one A and two A's, there is a spot missing on the first one. You have to see something. It can be bottom. You see the tick. You always see the tick.
No. But the point is that for me, the equivalence is the two tracks should have the same number of A's. But they don't have to be synchronous. I just count how many I see on each track. And so at some point they're different. And then I said, oh, okay, it was just late.
Sure, I see.
I did receive the reimbursement for Simon Institute for my travel, but it arrived a week later. But I'm okay with that.
Yeah, I see.
So this is, but the point is, I think we should move on. But this is a strong condition.
Yeah.
And there are different intuitions about it.
Yeah.
Okay.
But yeah.
Okay, let's move on.
But by the way, it's a condition that is satisfied by the model of Rife, and so it's not. Yeah. Okay. But sure. Yeah. It's a condition. So now the next step is how to ensure that, or what happens if these conditions are not satisfied, and so on. Yeah. So I mean, synchronous, we have it, but now what about perfect recall? So I think Moshe mentioned it, right? So now I just take the contrapositive. If in the future we are indistinguishable, then in the past we were also indistinguishable. There's another way to say it, and it reflects in the automaton in the fact that we are always accepting until we are different, and then we reject forever, whatever the continuation is. So this is sometimes called a safety automaton. So it's a very special class, safety automaton. But then comes the fact that this relation should be an equivalence, and this also we should ensure. So there are three conditions. The first condition is that it should be reflexive. So it means that if I read two times the same history on the two tapes, I should always accept, right? Because the history is indistinguishable from itself. And you can check in this automaton, you just read pairs of letters that are equal, so AAs and BBs, and you can see that you will loop between Q1 and Q2. So here, this automaton defines a reflexive relation. And that's not difficult to check, right? You just explore identical letters and you check that you don't reach a rejecting state. Now, the second condition is that it should be symmetric. If tau1, tau2 is accepted, then tau2, tau1 should be accepted. So the question is this, on this example, do you think this is the case? Is this relation symmetric? And how would you check it?
Checking what?
Well, whether the relation defined by this automaton satisfies this condition, that it is.
Well, trivial decision, probably.
Sure, yeah. For you, it's trivial, but I don't know if for the rest of the audience it is. So yeah, it's very easy. Yeah, you just okay. So what you do is you take two copies of the automaton, of this automaton. In the first copy, when you read AB, in the second copy you will read BA. And in this copy, you check that you can never reach a state where the first one is accepting and the second one is not. So if you do this check on this automaton, it's not very easy to see, but it will be symmetric. And then there is the third condition, which is transitivity. And if you have understood this one, I think transitivity will be also simple. Because you take now three copies, when you read AB in the first one and you read BC in the second one, you will read AC in the third one and check that you never can be accepting in the first two and not accepting in the third one. Again, yeah, just a cubic algorithm basically because you have three copies. And again, this automaton will be transitive, define a transitive relation. But this is very, very difficult to see, I would say, intuitively. And when you try to draw examples of two-tape automata that satisfy this condition, it's the transitivity which is the most difficult to achieve. If you draw a random automaton, it's almost impossible to make it transitive. So it's very difficult to grasp this notion, and you will see it play a role in the rest of the talk. But yeah. So okay, now we verify these conditions, and now we have a reasonable indistinguishability relation. Okay, now, as I mentioned, there is the question of expressiveness and comparing these models. So is it the case that you can express one model into the other, or the other one into the first one? Right. What's the relation between these two? So There is one direction which is not too difficult. And I don't know if it's... So if I give you the observation model, how would you construct the two-tape automaton to define the same indistinguishability relation? Well, it shouldn't be too difficult. So you say that they are indistinguishable if they produce the same observation. So you just read the two histories in two copies of the observation automaton. And as long as the observations are the same, you say, yes, we are indistinguishable. And once the observations are different, you say, oh, we are distinguished forever. And this is exactly, so this is this example. And this is exactly how I constructed this automaton. That's why I'm sure that it is transitive and symmetric and so on. You can see that these are just the pair of states, P1, P2, P2. This is the product. Okay, good. So yeah, this is an example. I mean, as long as the observations are the same, you accept. And then when you have AA, and this is an example maybe to give you intuition that you may have the same continuation, and now the observations are different, so you distinguish. Yeah. Good. Now, what about the other way? Going back from distinction to construct now this model. This is a bit more difficult, and it's actually very interesting because it will force us to define new notions and to play a bit with these ideas. So I'll define an information set, which is just an equivalence class of this indistinguishability relation. So given a history, I write it like this, the set of companions of the history. That's just an information set, an equivalence class. And now there is a natural successor relation between information set, which intuitively means if you are at a history that is here, that belongs to this set, what information set can you see when you are playing one more move? So actually, what is the information set of a successor of the history where you are? Well, it means that you are at a companion of Tor, and you read a new move. And then this information set might be the new information set that you get. Yeah. So this is the successor relation between information sets. And now you can see that this is acyclic because the length of the histories increase. And so you can never come back to an information set that you have seen. And it is backward deterministic in the sense that once I give you this information set, the parent must be the equivalence class of Tor prime, which is the equivalence class of Tor. So backward is deterministic. So this forms a tree, the information tree. And so one way to assign an observation to a history is to assign basically the node in the tree where you reach by reading that history. And so for a history, you could say, the observation is just the sequence of the information set of the first letter, of the first two letters, and so on. For each prefix, you output the information set. That would be one way to define an observation function, but this is not finite state because these things are increasing. So you need more and more observations to do that, a priori. So is there a way to do it with a finite state representation? Well, let's take some examples. So here I show you the observation automaton and the two-tape automaton. So here it says when you read an A, when you see an A, when there is an A, you see a 1. When there is a B, you see a 2. And this is the two-tape automaton. So what is this relation? Yeah, not really, yeah. Yeah, identity, yeah, exactly, yeah. So it's sometimes called perfect information. Yeah, it's perfect information. Yeah. So every information set is a singleton, and you are indistinguishable only to yourself. So yeah, it's identity. So here there is nothing difficult. Now, what about this one? If you see an A, if there is an A, you read a 1. If there is a B, you see a 1. Yeah, it's like every word of the same length is indistinguishable from each other. So you just have just one branch, and it's sometimes called a blind game. You don't distinguish anything, just the number of ticks. Now, our example, which I showed before. So here, the information tree looks like this. And, well, you can see that, for example, this node has only one successor because A and B are indistinguishable. But some nodes have two successors. And then later, you again have nodes with only one successor. So you can have one or two successors. And this is not surprising because if you're at an information set and you want to distinguish, you need to get a different observation. And you can get only observations 1 and 2. So at most 2 successors you can have, right? Because, yeah. And sometimes, like here, you have only one observation possible, so only one successor. Okay, now I give you the two-tape automaton, but I don't give you the observation model. So we'll try to see how we do that. So now the moves are A, B's, and C's, but we will first look at the left part of the automaton, which has only A's and B's. So when I have A, and B, I have to accept. But when there is a difference between the sequence of A's and B's, then I remember it by going to this state, but I still accept. And now whatever A's and B's you read, they are still indistinguishable. So as long as A's and B's are concerned, this is like a blind game. Everything is indistinguishable, like we have seen before. So the interesting part is when a C comes. And a C is like a check. If there was a difference between the sequence of A's and B's, and a C comes on either of the two tapes, then you will distinguish. So it's like you reveal what was in the past. You can see the difference when the C comes. Then you need also to deal with the case, okay, if there is a C on both tape and they were equal, you have to accept. And this is for reflexivity. You need to accept when the two symbols are equal. And then we need to deal with the case where there is a C on one tape. I mean, the difference comes exactly when there is a C, and then we also consider that this is distinguished. Yeah? If there is a check and the other guy doesn't check, then it's distinguished. So now how to construct the observation automaton for this? Well, the good thing is to look at the information tree. So as we have seen, if you have only A's and B's, you have this branch, which is the blind game. But whenever a C comes, everything becomes distinguishable. And so all the classes, they explode or so. And you get as many classes as there are words. Still finitely many at every level, but more and more. Right? Here 2, here 4, here 8, I guess, and so on. So now how can you do that with an observation automaton? Well, the point is you cannot, because this has unbounded branching, right? The more deep you go in the tree, the more the number of successors increases. Still finite, but increasing more and more. So there is no way with a finite number of observations to make this distinction in one step. And so there is no finite automaton that can define it. So this shows that this model is more expressive than the observation model. Okay, so this is the situation. The distinction model is strictly more expressive, and yeah, you cannot go back. And now there is a natural questions that you can ask is, can you decide if I give you a distinction automaton, can you transform it into an observation model? And yeah, this is also very interesting to manipulate these concepts and to play with it. So I'll give you some words about it. Any question at this point? Yeah.
So is it true that the observation model is always more precise, or it's incomparable in terms of like succinctness? I mean,
in terms of
succinctness, because like in your example, like the distinguished model has more state, the structure is like more complex. Do you have this kind of result?
I don't know. I don't know if it's more succinct always, or could because it could be that you dig the product, but then you can minimize the automaton and it becomes very small. But I don't have a general. This is not a question I would know the answer, so it's open. I don't know. Yeah. Okay, so now to decide this question, so I give you a distinction automaton. Can you transform it into an observation automaton sometimes, and can you decide when it is the case? Well, there is a characterization which is
This feels to me, I haven't formalized it in my head, but it feels related to distributed synthesis. Is it?
Yes. Yes.
Okay.
But related is very general. So, but I'll talk about distributed synthesis at the end. So we have already seen that if it's unbounded branching, then you cannot define an observation model, an equivalent observation model. And the characterization here says the other way is true. If you have bounded branching, then you can define it as an observation model. That's if and only if. And we have basically already proved an intuition of one direction. Now we need to prove the other direction. That when we have bounded branching, then it's possible to actually, with a finite state machine, assign the correct observation to the successors. And for that, it will be very convenient to, actually, it will be very difficult to, it's difficult to manipulate these information sets because they are sets of histories. So how an automaton can manipulate this is not easy. It's much easier to manipulate just a single history because that you can add a move and transitions through the automaton. And so we will represent an information set by just one representative. It's just one history. And we choose, for example, the smallest lexicographic element of the information set as a representative. We can fix an order on the letters, and then there is a lexicographic order. And we take that's our representative of the information set. And now we will work with representatives. That will be easier. So just to show again the examples that we have seen before, now I show you not the tree, the information tree, but the tree of representatives. So for perfect information game, it doesn't change anything because information sets are singletons, so the representative is just the single element. There is no choice. For blind game, it becomes something like this, right? Just the smallest word in the information set. For our example, it looks like this, okay? And what is maybe one point to see is that this is not a subtree of gamma star. For example, you have here A, which is the smallest element of the class AB, and here you have BA, so it's not a successor in gamma star. It's not that you just up and the move and you have, pruned the gamma star tree. It's just a bizarre tree as compared to gamma star. But otherwise, it's just well defined, and this is the tree. And this is the example for this unbounded branching. You have the blind thing and then single words here. Okay, so now how to use this to decide if you can, how to use that to construct the observation model when the branching is bounded. Well, the first thing is that we can recognize this notion of being a representative. So we can, this is just a negation, but automata are closed under complementation. So when it's not a representative, it's when there exists a guy who is lexicographically smaller and is in the same class. Then tau is not a representative of its class. So this is just, this is our two-tape automaton. This is lexicographic you can recognize, and projection, just a non-deterministic automaton. And this gives you the negation of being a representative. So if you take the complement, you have the definition of representative with an exponential because you have non-deterministic automaton, you complement. So the last thing we will need to navigate through this tree is the notion of sibling. When our two representative represent sibling information sets, and that's very easy. Two representative are siblings if their parents are in the same class. So this we can also recognize with a two-tape automaton. You just forget about the last word, the last move. And now the idea is very simple. If you give me a history, I will just want to know this class, is it the first, the second, the third child of its parents? So which sibling are you? And then I will assign it observation 1, observation 2, or observation 3. And this now I can do with an automaton. I will say that the observation of history is k, so which means I'm the kth sibling. If I have k siblings smaller than me, but I don't have k plus 1 siblings smaller than me. And what does it mean to have at least k siblings smaller than me? Well, it means that there are k guys strictly ordered by lexicographic order, such that they are all representative of their class. The last one is myself, is equivalent to myself, and they are all siblings between each other. So that means there are at least k guys, k siblings before me. And if there is not k plus 1, then I can really assign observation k, and this I can do now with an automaton, which is multiply exponential, but we don't want to go in this for the moment, at least. So now, if it is bounded branching, I will always be able to do that because, assuming I have the bound, because then I can just construct this automaton and have this quantification up to capital K. So now to this, so this is the characterization. Now we still need to decide: is it bounded branching? Yeah.
I would have approached it differently. I would say the information set is, if I read a word, the information set is all the states the distinction automaton can be in for any other track, okay, or two sets. Okay.
Yeah.
And that's immediately give me also a finite-state transducer, and now I have to check whether they're equivalent. So to me, I could do it seems to me I could do the whole reasoning just thinking directly about the automata. You see what I'm saying?
Yeah, I see what you're saying.
The transducer would give you the set of possible set of the DFA. Now you have to check whether this transducer is equivalent, give you a distinction that is equivalent to original distinction automaton.
I see.
Is this wrong?
I don't know, yeah. I don't remember now. I mean, I'm sure we tried this. So I'm sure we tried this because otherwise we wouldn't have gone through all this complication.
No, that's I would say that's to me the
Sure, yeah,
straightforward approach. And if it's wrong, we need to refine the intuition to understand why it is wrong. Because it is much simpler than the reasoning you're doing here.
But I don't see immediately why it is wrong, but
Okay, let's follow up
I
later.
need to think, yeah. Maybe, I don't know, yeah. It's too old, yeah, so to remember, yeah. But so what I was saying, yeah, is that now we have this characterization. One, it is bounded branching, then we can construct the observation model, the observation automaton. The question is, can you decide if it is bounded branching? I give you a two-tape automaton, is it bounded branching? And this is actually not an easy problem. So we would think, yeah, I don't know. But I don't know, it's not hard, I don't know, we don't have hardness, yeah.
Maybe the observation tree has bounded branching. Okay. Is it not the case that in your model, observation tree has bounded branching?
Yeah, but he wants to check if it's true, right?
It may not be equivalent to the original thing. So I say let's construct it.
Then verify.
Observation tree.
Yeah.
And
Check whether it has the same.
okay, this would be the.
Yeah. Maybe, yeah. Maybe, yeah. I don't know, yeah. But so still, it's interesting to see what happens. So as I said, the information set, it's easier to manipulate as a representative. And then what is cool is that we can also represent the successor relation by talking only about the representatives. So you remember the successor relation between information sets. This translates into successor between representatives. So tau is a representative of this guy and tau prime c of this guy. And when is there a relation? Well, when their parents are, the parent of this guy is in the class of tau, and both of these guys are representatives. So I can represent this again by a two-tape automaton. And now the question is, given a tau, how many successors can I have? And this is like the number of, I don't know how to call it, companions, but images of tau by this two-tape automaton that recognize this relation. How many guys can I have? And I want to know across all histories, does this number grow unboundedly? So it's the branching degree of this relation, and it's sometimes called the valuedness of a two-tape automaton. And now we use this, there is a result of Weber that the boundedness of valuedness is decidable in polynomial time, in the size of the automaton, and the bound is at most exponential. So once it is bounded, the bound is, yeah. But now this two-tape automaton, it has representatives, so it's itself exponential and so on. So there are many exponentials involved, and we are happy with decidability, but we struggle a lot to solve this. So I hope, yeah, I don't know if your solution works, but so in the end, the decision problem is EXPTIME because this automaton is exponential, and we use the procedure of Weber, which is p-time on that automaton, so it's exponential time. But then the bound becomes doubly exponential, and the construction that we have here is itself doubly exponential in k, so it's fourfold exponential in the end, but it's not important. Yeah. So, yeah.
It's good news. It's most for.
Yeah, that's the good news. Yeah, we have a bound. But yeah, so definitely this is not optimal. So we have an improvement over that, and I will give you a few words about it. And we have no lower bound, so we don't know. It might be that your solution works. Yeah. So in fact, yeah, I don't really. So I'll skip this. So in some sense, I don't want to really now show you a threefold exponential solution and so on. But I just want to mention one property that will be useful to improve this construction and to go towards the threefold exponential, because this property illustrates a phenomenon that occurs a lot in this work, in this research program, which is that I will show you a property that is very simple to state. It's also very simple to prove. It's really a few lines, and it doesn't use any complicated technique. But the intuition, it breaks my head. So maybe Moshe will understand it, but for me, I don't understand it. Although it's a very simple result and very easy to prove. But I'll show you something. And yeah, so this was just for the sake of beautiful theory, I would say. So now we are back with the two-tape automaton, and I will define what I call the reflexive states. So what are the reflexive states? They are those states that you can reach by reading from the initial state 2 times the same history on the two tapes. Okay, so we have seen that this will always be accepting. And what are the states that you reach? In this example, it's Q1 and Q2. Okay, that's clear. Now I'll define another set, which I call ambiguous states, and you will see why. So what is an ambiguous state now? It's a set of states from which, by reading the same history, you reject. So maybe this will break your intuition, but so now, yeah, so definitely, so first let's look at an example. So you see that here you can read AA and reject. Here you can also read AA and reject. So these two states are ambiguous. So it's clear that those cannot be ambiguous because when you read the same history, you always accept. So, okay, so that's my definition. Now, just a small hint of why this is useful, these ambiguous states. It's towards constructing an observation automaton for it. If you imagine that you have two histories that are indistinguishable, means if you want to have observation, they have received the same observation so far. And suppose that these two histories get you to ambiguous state. So for example, AB. Then the observation automaton that would represent this relation cannot be in the same states by reading tau and tau prime, because after that you will read the same letter, and therefore you will output the same observation. So it cannot be that you can now you should distinguish them by reading the same AA, but you cannot if you are in the same state. So this gives you a condition that the observation automaton needs to separate these two histories. That's why this notion of ambiguous state is important. And of course, we need to develop much more concepts to come up with a construction, but for the moment, that's it. And now here are the two properties. One of them is really not easy. So the first one says, okay, these two sets are disjoint. And I think on the example, it's already clear that from the reflexive states, you cannot reject, so you cannot be ambiguous. But what breaks my head is that it's actually a partition. The union of these two sets is the whole automaton. And it's a 5-line proof. But it requires two things. One is that the automaton is minimal. It's only true in the minimal automaton for this language. And then it requires the transitivity. It uses the property that indistinguishable relations are equivalent, and therefore it's a transitive relation. And this I told you that it's difficult to grasp and to draw an example which is transitive and so on. And that's why it's not very obvious. But this plays an important role also in improved construction of the observation model. So yeah, and it's a partition, and yeah, so you have it. So I think I wanted to skip this part and jump to the distributed. So I will not say any word about synthesis, at least not in detail, maybe just at the end. And now I want to present the application of this model, which is, yeah.
If you have a distinction automaton that doesn't give you, there's no underlying, not equivalent to transducer.
Yeah.
Is synthesis decidable?
So we don't know that. We don't know that. But the application that I will show you cannot be expressed by an observation automaton. So it's more general than Reif. And this one is decidable. So we have at least something more expressive and still decidable. But the more general model, I will just show it at the end. It's not, we don't know. And yeah. Okay, so now I will just say a few words about full information protocols. So you remember the first slide. It was horizontal, now it's vertical. Synthesis problem is to construct this box that transforms inputs into outputs and satisfy the specification. Now I will, in the rest of the next slides, I hope you see the colors. So I will color the input in blue and the output in red and say that the specification speaks about the input and the output in this way, just to mention that this is what we do. So now if you talk about distributed synthesis, you would have multiple boxes like this. Each of them has an input and an output, and in general, each of them can talk to each other. So I draw this communication channel. And if you want to be as general as possible, the specification will talk about the input, the content of the communication, and the output of each process. And synthesis is to construct a strategy for each process such that jointly they satisfy the specification. Now this is, I suppose most of you know, undecidable already when you have this configuration with two processes and there is no communication. So this we can model with the spec by saying that there is a communication, but the spec forces you to always communicate the same symbol, for example. Then it's equivalent to no communication. So if the spec says this, then you have this situation, and this situation is undecidable. It's old results. And basically, the only way to get decidability, I mean, it's not really the only way, but the usual way to get decidability is this pipeline architecture, where only this process has an input, then it talks to these guys, and then the last guy has an output, and the spec talks about the content of those channels. And why this is decidable is because you have hierarchical information. So whatever this guy knows, it's because this guy told him. So this guy has more information than this guy. He knows the input and he knows what he told to this guy. So, and we can continue like this. Each guy has more information than the guy on the right. And once you have hierarchical information, decidability follows, and it's basically an if and only if by the work of Berndt-Fichtbeiner and Sven-Chevet. They showed that, they have a criterion that's called avoid information fork, avoid, incomparable information between processes, and then you will have decidability. So this is basically close the problem. It's an if and only if, and you know when it's decidable. So then what people have looked at is a different model where there may be communication, but then the communication is not constrained by the specification. Once there is a communication, it says you sent all what you know. So you cannot decide what you sent or what you don't send. So it means that now the specification talks only about the inputs and the outputs. It cannot constrain the communication. And then you see that again, actually, one of the guys has more information, and it's this guy who is more informed now, because he knows his input, and he knows everything that this guy knows, because this guy, whatever he knows, he sends this to this guy. So there is again hierarchical information, and it's again decidable. And this is sometimes called an external specification. It talks only about the inputs and the outputs, it doesn't bother about the communication between internal to the processes. And now they generalize this to what they call well-connected architectures. As long as it maintains a hierarchy of information, it will be decidable. And so we got inspired by this, and also by a notion of full information protocol, which is something studied in distributed system community, which I don't know very well, but Dietmar knows, and he had this idea. So now we need to be very careful. But what we will do is to say that the communication here may be unreliable. It may crash, it may be repaired, it may crash again, it may be repaired, it may crash forever. But there is a flag that tells whether it is active or inactive, and the specification, that's why it is hatched like this, the specification can talk about the status. And for example, say that if a link is active infinitely often, then you have to ensure something. But if it's crashed forever, then of course, you don't have to do anything. So the specification can talk about the input and the outputs, and also about the status of the link. And so, as before, as in the previous slide, when the link is enabled, then you have to send everything. You cannot choose anything. And now the last thing is that we want to avoid also that the specification says, oh, the link is crashed, and now we have two processes without communication. If there would be an input and an output to both, it would be undecidable again. So we have to constrain further by saying that only one of the processes can be constrained. Only the input of one process can be constrained by the specification. The others, their output cannot be constrained. So it's a kind of a restriction as well, but still I think quite interesting. And so all in all, what we have is only one process which is really active in the sense that it can choose its output, and the other, they are inactive. They're not really active because they have no choice. They receive an input, and then when the link is active, when the communication is active with someone, they have to send all what they know. And that's it. They have no choice, really. So I say that one process is active and the others are passive. They are just observers here.
So suppose the link crashed for 1,000 times, and then 1,001 is open. You sent all the history that happened before in 1,000.
Yes,
okay.
And I will exactly illustrate this now.
Yeah.
So because we need to be clear what it means that you send all you know. And this is this example. So imagine that, so this guy is isolated from the rest of the world. So the link is crashed. And then for many steps, it is crashed. But still, it receives an input, right? A1, A2, and so on. And now suppose that after n steps, whatever n is, the link become active. So it's exactly your question. Then sending all what you know means sending all the inputs that you have received. And this means sending a finite message, right? The set of inputs that you've received so far. But this finite message can be arbitrarily large because this repair can happen arbitrarily late in the execution. So it's something unbounded, It's an unbounded communication. So I think this just summarizes, So we have an arbitrary dynamic architecture with links that can be enabled or disabled, the external specification, one active process, n minus one are passive. And you can think of this, so you can think of this as a sensor network. So you have many sensors spread all over, they gather information, and once in a while they send you information. whenever the link is active. And then they send all what they know. You don't lose packets. So now the final point and the connection with the previous part is that, so you see there is only one active player. So it's again a two-player game in a sense. We try to synthesize this strategy, and that's all, because the others, they don't have choice. And so what is interesting is what is the, well, because really only this guy has a choice to choose the output. The others, they are passive. They receive an input. Yes. Yes. The spec speaks only about the output of this guy. So it's very restrictive. It's not, I would not even call it distributed synthesis anymore because of this. But still, you have many processes and they communicate. So, and hierarchical information is gone because they receive their independent outputs and so on. So it's, But what is interesting, what is interesting is what is the indistinguishability relation of this guy? What can he not distinguish? Well, when you have this sequence of inputs here, no matter what they are, he will not distinguish, right? Because he is not connected to this guy. And when the link becomes active, then he can see it. It is revealed. So it's exactly like this example of the first part. You don't distinguish anything, and then suddenly you see the light. Okay? So it means that the indistinguishability relation of this model, because of this message size is unbounded, will also have unbounded branching. Right? So you cannot just reduce to Rife and solve it. And that's, I think time is almost over, but I will just conclude with a preview of the results that I didn't talk about. So in terms of expressiveness, we have seen that the observation model of Rife is strictly less expressive than the two-tape automaton distinction model. And we have seen that FIP, this full information protocol model, they have unbounded branching information tree, so they are more expressive than Rife. Definitely, you cannot reduce them to Rife. They have unbounded branching. And it turns out that each time you add one passive process, you have one more level of expressivity. So it's a strict hierarchy. And there are also guys that are here that are not expressible by a FIP with any fixed number of processes. So very interesting in terms of expressiveness. And then in terms of decidability, this was the question of Moshe. So the general problem, we don't know if it is decidable, but there would be many things to say about it, and I skipped it. And then when you have n processes, we have an n+1 x-time upper bound, which may be not surprising for many people who have seen distributed synthesis. It's usually like this, and there is n x-time behavior. But what is also breaking my head somehow is that we also have the lower bounds. So it's n x-time complete, or n plus n x-time complete. And also every full information protocol indistinguishability relation can be expressed as a two-tape automaton at the cost of an exponential only. So it means that the lower bound that we have here carries over here. I mean, okay, there's an exponential that you lose, but it's n x-time complete for every n. So it means that this is n-1. This means that this is n, just one level less, x-time hard for every n. So it's non-elementary hard. And initially, we thought this would be easily decidable. And so when we thought that it's non-elementary hard, we were very surprised. But of course, if it turns out to not be decidable, then maybe it's not very impressive. But I can't believe that this is not decidable. So it's such a simple model, but it could be. It could be, I don't know. It could be undecidable, So, but still that it is non-elementary hard. And I think I can skip this and turn to your questions. Thank you.
Thank you for this nice talk. For the full information, what was the P process protocol? You said the phi, this formula phi, is the specification plus link status. Can you say what is the meaning of this plus link status?
So you can think that there is a for each link there is a variable, a Boolean variable that says the link is active or the link is not active. Okay.
And so you may use in this formula phi any combination of these.
Yeah, you could say, for example, if all the links are active infinitely often, so if this flag is set to true infinitely often, then you have to satisfy something. But otherwise, of course, if the environment, crashes all the links, then you don't have to satisfy anything. So the specification can tell that. You need to grant every request if the link is active infinitely often or is always active or whatever. Yeah, you can talk about it.
So thank you for the talk.
So I thought that if your specification would not talk about these inactive links, then this would have some flavor of asynchronous communication, because you transmit the whole path whenever you can. So it's like a delay, yeah, asynchronous delay.
Yeah. So, yeah. I mean, yeah, there are works in asynchronous where they do this kind of thing. Yeah, there's this causal memory.
No, but even without causal memory, I think the band was also working on this on the Punelli-Rosner model with asynchronous communication.
Yeah, this Petri nets thing, right? You have this, yeah. It's related. Sorry.
Yeah, so I was also wondering about that. I mean, in Petri games, so the model with causal memory, you also have this idea that you transmit all the information you have when you synchronize, right?
Yeah.
And there are these results that if you have one system player and an arbitrary number of environment players, which resembles your setting, right? Then the problem is EXPTIME-complete, and it doesn't get worse than that.
Yes.
Whereas you seem to have this hierarchy. Do you know why that is?
No, that is also something very puzzling. Yeah, and I saw your papers on this work, and I think when we wrote this, we also mentioned that there is this difference, and we don't know really. That's one of the open questions. And we talked also to other people who were working on these similar things, and they also said that it will be EXPTIME when they have this only one active player. But here we have this lower bound, which is very convincing. So I don't know why. Yeah, I don't understand really. So, but this is there are many open questions in this work. It's really ongoing work, and there are many things we don't understand. So it's definitely ongoing. Yeah.
So in the FIT model, if the link comes up for one step, right, then within that sort of one tick of the clock, you can transmit an unbounded amount of information. It seems a bit unrealistic for practical systems.
I don't see. I mean, like, I have this picture of a satellite which is around the moon, and then when it comes back, it sends all this data, and then I mean, okay, sure, it's an abstract model that you can gather this, and then you go on to the next step. I don't see. I find it reasonable, but yeah, sure, it's a simplification of the reality. Yeah.
Follow up on this. If you have the indistinguishability as a tool, why not go the opposite way and limit what one process can know locally, as opposed to have to pass all the information to maintain hierarchy? As in, you would forget your input. I was wondering, because I have the wrong intuition apparently about this, so I'm wondering, can it be used to sort of enforce something like that? That you as a process would forget your own inputs?
Well, okay, I don't know. So there would be a natural question, which is, once I give you this FIP and sometimes you have unbounded message to transmit, one natural question would be, can you do it with the bounded message transmission? That's what I meant in the beginning with communication. Can you do it with bounded communication? Maybe sometimes you can. You don't need to send all your data. So it makes sense, but I don't know.
I guess I'm asking something far more fundamental. You said that undesirability is if and only if you don't have hierarchy. Yes. Right? And then it's being fixed by basically forcing someone to send everything they have, so that now that person knows it strictly more. Yes. What if the local process can forget information? Then you may be able to maintain hierarchy by basically, as opposed to you passing on everything to someone else, you forget things. Therefore, you know less. For example, you forget your entire input. You just know the last bit.
Yes.
I mean, I thought either the observation model or the indistinguishability should be useful for encoding something like this.
Let me elaborate. So every agent, you say, could be must be finite state, let's say.
Well,
and then this full information will be the transmitter local state. Kind of what you're asking, right? Yeah, the transmitter local state. So it's always finite, but it's everything they know in some sense.
Yeah, but this is less powerful than this model, right? Because imagine that you have two processes that you can talk to them, but for the moment you are disconnected, and you want to know if they receive the same input. If they just transmit their local state, when
you don't know if they transmit.
No way to. Yeah. But if you can receive the entire sequence, then you can compare. So it's not always possible to do it with the local state, but it's a very interesting case. And that's what I'm saying, that maybe you want to decide, okay, you have a complicated protocol, but can you do it with transmitting the local state of some automaton? And that's a very reasonable question. And yeah, we're also considering this, but for the moment it's...
I mean, I have to say the distinction model just feels to me like the classical fork. I mean, I don't know. I mean, you probably have thought harder on it to see if there is a reduction there, but that's what it feels like.
Yeah, we were also puzzled because we have this nx time bond, and we thought it will be we can reduce from pipeline, for example, or from asynchronous. There is also work on asynchronous where they have also nx time bonds, and we were not able to redo the reduction. But of course, such a reduction must probably exist. But we were not able to connect these two models. So again, yeah, maybe we just didn't see it. But yeah.
Okay, let's wrap it up. We have time in the afternoon for more questions. So let's thank.